So I'm going to introduce Dr. Stephen Chu. Stephen Chu is the William R. Keenan Jr. Professor of Physics and Molecular and Cellular Physiology at Stanford University. His research spans a very large amount of science, from atomic and polymer physics, biophysics, biology, biomedicine, and batteries. He shared the 1997 Nobel Prize in Physics for laser cooling and trapping of atoms. From January of 2009 until April of 2013, Dr. Chu was the 12th U.S. Secretary of Energy and the first scientist to hold that cabinet position since Ben Franklin. During his tenure, he initiated ARPA-E, the Advanced Projects Research Agency for Energy, the Energy Innovation Hubs, which had a profound impact on our national labs, the Clean Energy Ministerial Meetings, and was tasked by President Obama to assist British Petroleum in stopping the Deepwater Horizon oil leak. Prior to his cabinet post, he was director of the Lawrence Berkeley National Laboratory, professor of physics and molecular and cellular biology at UC Berkeley, the Theodore and Francis Gabal Professor of Physics and Applied Physics at Stanford University, and head of the Quantum Electronics Research Department at AT&T Bell Laboratories. Dr. Chu is a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, Academia Sinica, and is a foreign member of the Royal Society, the Royal Academy of Engineering, the Chinese Academy of Sciences, and the Korean Academy of Sciences and Technology. He has been awarded 24 honorary degrees, published more than 250 scientific papers, and holds 10 patents. Let's give Dr. Chu a warm welcome.
Having a technical issue because the audiovisual guy refuses to let me help, and I want him to get the screen bigger, so it fills up the screen. All right? You're saying that's not well? Okay, fine, good. I quit. All right, so let me begin by talk as it's very typical of my talks. It's prepared almost just in time. And is this controlling it? All right. So let me first talk about some common misperceptions of what I think about inventions and how they're related to discovery, invention, the taking of the invention into an innovation, which eventually, if successful, actually goes into the market in a big way. In actual fact, there's really a back and forth interplay between discovery and invention. Quite often scientists, when they want to do some new science, actually realize they have to invent a set of new tools and say go about doing that, motivated by the science. Once you have an invention, not all inventions get picked up, and so we define innovation as something that actually has a chance of getting into the marketplace. And once it's in the marketplace, other scientists and other engineers can use this invention and innovation to do further science. Now, coupled with all of that is market transformation, but you should also say that it's not all driven intellectually. Over the last, especially the last decade and a half, I've discovered you can have great invention, great innovation, and the incumbent industries will make sure you never see the light of day. So let me define what I call the difference between a transformational and a disruptive technology. Around the beginning of the 20th century, the existing technology was the horse and carriage. And there were some emerging potentially disruptive technologies, People played with the steam-powered vehicle. The Benz motor wagon was invented. There was actually electric vehicles being invented. And these were what we called transformational. But the disruptive one was the Model T. Also, just for your knowledge base, electric vehicles were competitive perhaps until the electric starter motor made starting an internal combustion engine easy for everybody. And that was a key invention. All right, so let me tell you about what becomes really disruptive. This car was the Rolls-Royce Silver Ghost. It cost a lot of money. If you were a professional lawyer or something like that, it would be 10 years' wages. It was a terrific car. It's 6-cylinder, 7 liters, at a 3-speed transmission, 48 horsepower. It set a record for longevity. It could go 50 miles an hour for thousands of miles. It wouldn't break down. And it also got 20 miles to a gallon. But it didn't transform transportation. The car that transformed transportation was the Model T, because it was Ford's vision that he really wanted to get this house to be affordable to a large cross-section of society. Now, I just wanted to put a quote there that it wasn't obvious Ford knew what he was doing. And when he was looking for investors, he was actually on his third company. The first company failed. The second company, he had personality conflict with the investors. He wasn't easy to get along with, so he went away and formed but he was allowed to take the name Ford with him, and his third company, he was looking for another set of investors, and the president of Michigan Savings Bank advised Henry Ford not to invest in the Ford Motor Company, saying, "The horse is here to stay, but the automobile is a novelty, only a fad." All right. The Model T engine was actually it's 2.9 liters, that's a misprint, 20 to 22 horsepower. Today, that's a Ford engine, 1 liter, not 2.9, not 20 horsepower, 123 horsepower. Not a dramatic invention, it was incremental improvements over a century. Ford, by the way, did not invent the internal combustion engine. He didn't even invent the assembly line. He improved the assembly line, okay? Another evolutionary thing, that was the first successful commercial jet, the Boeing 707. To the uneducated eye, you know, the 787 looks kind of like the 707. No progress for 50 years. Actually, I read a newspaper column that said exactly that. It's an op-ed piece, I think, in the Wall Street Journal. Okay, what's the difference? The 787 uses 30% of the fuel of a 707. It carries 70% more passengers. Those two engines have twice the thrust of the 4 engines of a 707. Other than that, they're the same. It's like the 2.9 liter original Ford engine with this other engine that, by the way, fits on 8.5 by 11 sheet of paper. That engine, that 123 horsepower engine. All right, so there are inventions driven by businesses. And the one that I am most fond of was Bell Laboratories. If you look at that picture of Bell Laboratories, off in the upper right-hand corner in those woods, I owned a house. I would hop over the fence. I would go to work. It was perfect because I spent most of my time at Bell Labs anyway. I should say that 15 scientists at Bell Laboratories went on to get Nobel Prizes. That in itself is remarkable, but it's even more remarkable because every one of those scientists was hired at the beginning of their career. They were not hired as stars, with one exception. Charlie Towns was already established, okay? But the rest were beginners. In a 3-year period, there was a bunch of us, 5 of us who were hired into a group of about 40 basic researchers, or 30, wasn't that many, of which 5 of us got Nobel Prizes. So there was something in the water. That was, you know, I too was young once. Now, I want to give you a brief history. So Alexander Graham Bell invents the phone in 1875. Just in case you're wondering, Alexander Graham Bell is the one with the beard. That's his family. He tries to shop his invention around because he wants to really have it disseminated quickly. He thinks it's a great thing, and so he wants to go to established people in communications. And of course, he goes to Western Union, which was running the telegraph, and they looked into it, and an internal memo was circulated saying, the telephone has too many shortcomings to be seriously considered as a means of communication. The device is inherently of no value to us. Then he went to the British Post Office, which is also in charge of lots of communication, and which the Brits declared, the chief engineer declared, Americans have the need of the telephone, but we do not. We have plenty of messenger boys. Very British. I should say that many, many great things came out of Bell Laboratories. The accidental discovery of radio astronomy, the first binary digital computer, which included all of information theory was invented by Shannon at Bell Laboratories. The silicon photovoltaic cell, the transistor, the laser, the transatlantic coupling, charged coupled devices, Unix, which is the underlying language of software of the operating systems of Apple and Google, the digital signal processor, satellite communications, cell phone technology, functional magnetic resonance imaging, which tells you which parts of the brain are lighting up when you're thinking of whatever you're thinking of, and wireless local area network technology. The list goes on. And I eliminate some of the more researchy stuff that got Nobel Prizes. Even Bell Laboratories, after that rocky beginning, didn't sometimes appreciate what it had. In 1980, Bell Laboratories invented the cell phone and the idea of cell phone technology, but they said, is this really going to be a business? So they hired McKinsey and said, by year 2000, how big is this market going to be? And McKinsey looked around and said, well, we don't think it's going to be very big. You may have 900,000 subscribers. This was a very sore point. I knew the engineers who developed this. I was at Bell Laboratories in 1978 to 1987, and they were very irked that their little thing that they gave birth to was going to be killed by AT&T, which it was. They killed it. Well, the rest is history. That's a lot of cell phones. They missed it by 2 orders of magnitude. And by 2014, there were 4.5 billion users. I should also say that when they killed it, they said, we're not going to invest in it. We're going to stamp out all the research. And then years later, I think when I was still at Bell Laboratories, or maybe shortly thereafter, they found that there's this little part of Bell Laboratories in Allentown, Pennsylvania, that was making a large profit. All the rest of Bell Labs and AT&T was losing money hand over fist. They said, what's going on here? So they said, why is this little thing making lots of money? Well, they didn't kill it all. That was the gallium arsenide solid-state devices, which were the radio frequency part of the cell phone that Motorola and everyone else was using. So they missed that. Okay, now, let me talk about invention driven by a vision of a disruptive technology. This could be a disruptive technology. It's a beautiful car. It's wonderful. How many people own a Tesla? Okay, around where I come from, half the people will raise their hand. But this is like the Rolls-Royce Silver Ghost. Without subsidy, it's the fully loaded thing is about $110,000, $120,000. And what you really need is a better battery. So I understand there was a talk on batteries, so let me give you a few insights. Many people don't realize, they say, well, batteries haven't made progress for the last 20 years. In fact, the people who say that most strongly are people in the automotive companies who make internal combustion engines. I was at a workshop in an EV Everywhere thing, and a senior engineer at Ford, we're at a table of 20 people. He said that so loudly, so confidently, and he said, no progress in the last 20 years, no progress in the next 20 years. That brown curve is the history of lithium ion, first invented by Goodenough, but first commercialized by Sony for laptop computers. The energy density per unit volume, which is the figure of merit for a cell phone and computer, is how many watt hours per liter, and it started roughly at 200. And by 2005, it's at 580. Okay? Now, I'm on the board of a company, and we're shipping out batteries over that, 700. And everybody is working on batteries with that density. So the point is from the early 1990s to 2010, the energy density, you can't sell a battery now at 500 watt-hours per liter. And the ones at 600 are now become such a commodity that the price has plunged, okay? There are people are still willing to pay big bucks for something at 700, 800, and 1,000. What about the price? So the energy density is going up. The price, we had a very bullish plan for what batteries for electric vehicles would be, and we felt we provided a roadmap. We're funding things that we think we could get by 2022 to a battery that would be about the manufacturing cost would be at about $150 per kilowatt hour for the battery pack, the battery, the cooling, the everything. That blue solid curve is Bloomberg New Energy Finance, which is usually regarded as a kind of a forward-leaning publication of optimistic projections. The X's are the real manufacturing costs, and the gigafactory, when it gets built, is projected to be here. Tesla is projecting by the end, when it's going to be finished by 2016, they hope, and that would have been 6 years ahead of our very aggressive schedule, but that when we announced it in the Department of Energy, they thought we were smoking something. And so if you look at what's happening, it's actually much faster than even the most optimistic people. When I got back to Stanford, I started working on a number of things, including batteries. And we've just submitted our 4th publication, but I'll tell you one strategy that we've worked on. This is with Yi Shui, who's in materials science at Stanford. He's been in batteries for a decade. And so we started scheming about ways to try to get a solid lithium metal anode. This is, in a certain sense, the holy grail of lithium batteries because it's the highest energy density, but also you gain more voltage. And so the idea was, in the top layer, you have blue and lithium metal, and there's something called an SEI layer. That's a solid electrolyte interface. Lithium's very reactive, and it forms a protective coating, just the way aluminum oxide quickly forms a protective coating, or silicon dioxide forms a few monolayers of protective coating. The trouble is, if you wanted to charge this battery, or discharge it, especially if you wanted to charge it at any reasonable rate, there could be imperfections in that SEI layer, and then there could be a little bubble of lithium that is this instability, that also in the bubble has a higher electric field, and it just grows unstably, positive feedback, and then you get this dendrite formation. The dendrites streak across, the battery shorted out within a few hundred cycles, or 100 cycles, it's dead. So nobody is able to make a solid metal battery. One of our philosophies, there are 2 we're pursuing, actually 3, but this one, there are 2 papers out on that one, is to substitute that naturally formed SEI layer with a nanofilm, let's say 10 nanometer 6, that readily allows lithium to diffuse, which has some internal structure. What we did in this first paper is we just put some polystyrene spheres on it. They self-assemble. After 3 layers, you evaporate carbon on it, you blow away the carbon, and that, as you see in the lower right-hand corner, that 20 nanometer thick carbon layer is actually quite robust. You can take it and you can bend it. And it passes lithium quite readily. On the upper part, we have a fake battery-like thing for diagnostics. We're using an electron microscope to see how the lithium is going into this metal, and the bottom left-hand little balls, we're actually taking electron microscope pictures of lithium going into these balls, and at not great energy densities, but up to a couple of milliamps per square centimeter, you see no degradation. Now, I have to confess, in full disclosure, at 5 milliamps per square centimeter, it's degrading. But we think we have ways around it. But the point is, it's a way, we think, of getting to a solid metal anode. Now, we are also developing in situ diagnostics, so we can use a water electrolyte. We think I think I can get about 10 or 20 nanometers of optical microscope resolution to see what's going on. And you really will need this as we develop these things further. It's in situ diagnostics in real electrolyte conditions. All right, the Tesla battery, the long-range one, even though I loaned them $460 million, they don't tell me their real secrets. So I'm guessing that their battery weighs 1,200 pounds, and I think my guess is good to about 10%. I'm guessing what the price is of manufacturing. It could be a little bit cheaper than this today. And so the battery is 1/3 the cost of the car, and it adds over 1,000 pounds of weight. So that's Professor Yishui. And so the current anode densities are here. They're carbon, and then carbon plus little sprinkles of sodium, and then finally silicon. And finally, silicon anodes. Silicon anodes can get an energy density up here. We're working on a metal sulfur chemistry where we think we can get here. I don't know whether we're going to get there. We'll know within 2 years. But it's going to have to be a self-assembled battery, but we think we can probably get 15 times the charging rate as well as 4 or 5 times the energy density. I don't know whether that's called disruptive or evolutionary, but it's a better battery if we get there. I think you heard this morning, I was told at lunch, that of course the metal air, lithium air, zinc air, are the big payoff. Even bigger challenges because of the huge changes in volume with this. I think we think we've got around the change in volume for the metal anode sulfur battery to go thousands of cycles. But this one is still, it's going to be a big plus. It could be useful for utility scale as well as for cars. But even at that, in between the red and the tan curve, all of a sudden your battery weighs less than the weight of an internal combustion engine. And then the cost, if we achieve that, will be comparable to the internal combustion engine. So this, we hope, would turn into a disruptive technology. I've been also working on biological imaging for the last 20 years, actually. And in this paper published in 2012, we were looking at biofilms. This is a cholera bacteria. Those little protrusions are proteins being excreted by the bacteria to form a biofilm. Virtually all chronic infections in the human body are due to biofilms. Your body immune system can't attack the bacteria once they've settled into a fort, which is a biofilm. So we were taking microscopic movies of these bacteria-forming biofilms. The thing on the left is what you see on a conventional microscope. The thing in the middle is what you see with these so-called super-resolution techniques. And if you blow up that little square, you see something like that. So suffice it to say, the imaging technology is better. Okay, but let me go on and say that, and the Nobel Prize in chemistry given to 3 physicists this year, that happens quite a lot, is due to the development of these imaging technologies, a very well-deserved Nobel Prize. So, but they're using dyes, using genetically encoded dyes or organic dyes, and they don't last very long. The dyes are unstable. And the best pictures that you get are the ones like I've shown, in rigid cellular matrices. If you try to label a protein in the cell or even on the cell membrane, the Brownian motion is so fast that it smears it out. You cannot get to super resolution. And so that's why the first experiments we were doing with rigid frame structure, you can get terrific pictures. So wouldn't it be nice if you can develop nanoprobes that would allow 10 nanometer spatial resolution, but where the light is coming in so fast, that you can follow the dynamics. That means you're going to have to take snapshots in 1 millisecond, not 100 milliseconds. And so, so I started casting around. There was some stuff on these so-called diamonds and silicon vacancies. They were commercially available, but they were really crappy. That's a technical word physicists use. And so I said, okay, can we make them? And then by accident, it turned out that I found a colleague, friend of mine from long ago, Ziek Shen at Stanford. He was, they found these so-called diamonoids. A diamonoid is a molecule of carbon in the form of a diamond. And they were found in meteorites. And so the question is, can you synthesize these molecules of carbon, and can you use those to be the seed to grow a perfect diamond in a CVD condition? And how small can you make it, and can you do all these other things? And so I'm not going to go into this, but we've been playing now for a half a year. It's in a microwave oven. The carbon source is methane. The microwaves, the ion bombardment breaks the methane down. It goes onto the diamonoids. We've now recently separated the doping from the growth from the annealing. So you have total control over the whole process separately. We also are now able to, these are big diamonoids. They're really crystals. This is a small one. Those little things, if you may not have the resolution to see this, but you'll see these little rows of balls. That's what's called a lattice image. You've now imaged columns of atoms. And with this lattice imaging technique in electron microscope, you can show that this is a perfect crystal of diamond, except it's a scale 6 nanometers. And it's bright. 10 million counts a second. Those of you who know about fluorescent probes, you will normally drool at 10,000 counts a second. We think it's photostable. Okay, and we're working on a process. We've got now a way to look at for each run, hundreds of particles, single particles, fully characterized by SEM, by lattice imaging, by X-rays, and by fluorescence of the same particles. So you can make an ensemble, a distribution of the particles. Previously, I found that you can take a few electron TEM images, but then you average the optical properties, especially with small stuff. So we've developed a method that we can actually now we know what we're doing. And it's a thing I've learned in 40 years of doing science. If you know what you're doing, you're more likely you can make progress. Let me talk about inventions driven by societal necessity. Well, you know, there was a number of inventions that truly transformed the world, namely the inventions that led to the Industrial Revolution, like the steam engine. This is one of my favorite paintings. That sailboat you see in the background it's an iconic warship that it was being broken up for scrap, and it's being towed to its final berth by a coal-burning, steam-powered tugboat, and in a setting sun. So it was the changing of the guard, so to speak, from sailing vessels to smoke-belching, coal-burning things. And here's an invention that was driven by a talk. The talk was given by Sir William Crookes, who, when he was inaugurated as the president of the British Association for the Advancement of Science, instead of the usual pleasantries of how glad he is and how happy he is to be there, he did that for the first 2 minutes, and then he said, "England and all civilized nations stand in deadly peril of not having enough to eat." So what did he mean by that? What he meant was that artificial fertilizer being imported from South America, saltpeter, was being used to grow crops at the rate they needed to feed England and Europe. But he just did a back-of-the-envelope calculation, said, hey, we're going to run out of saltpeter within 20 or 30 years. So unless we can do something, we can't feed the population. Manure was not good enough. So then he said, it is the chemists who must come to the rescue of threatened communities. It's through the laboratory that starvation may ultimately be turned to plenty. What was he talking about? Can you fix nitrogen to make ammonia and use the ammonia to make fertilizer? And then you didn't need the saltpeter. So it would be a chemical synthesis process. That set a race going among all the great chemists who knew about catalysis. The person who won was Fritz Haber, who got the Nobel Prize for chemistry in 1918. He did this work with Carl Bosch at a company called BASF. It's the largest chemical company in the world. Started with colors and dyes, but this was deemed so important, and they also realized maybe Carl Bosch should have shared it. They gave him a second Nobel Prize. And they said, well, for the invention of high-pressure, high-temperature catalysis. Well, I'm sorry, that was actually done with Haber. But it was deemed so important an invention that in 2007, Gerhard Ertl got a chemistry prize for heterogeneous catalysis. And in the citation, the Nobel Committee said, at last, we're beginning to understand the Haber-Bosch process. Okay, that's how important this was. Because it enabled you to make fertilizer, you can feed the world. Now, what it did is it enabled you to feed the world, so the world population grew. And let me also, so by the 1960s, it was looking like artificial fertilizer wasn't enough. Land use was becoming an issue, and people were projecting, again, mass starvations. So Norman Borlaug in the 60s was inventing ways of breeding different strains of wheat. And you see on the right-hand side pictures of a strain of wheat that Norman Borlaug hybridized. The one on the left has these really big kernels. The one on the right has mostly stuff that you don't eat. And he actually had to hybridize the wheat plants so they were small, short, with very thick stalks, because the wheat was so heavy they would just go over and crush. And so he got the Nobel Prize in 1970 for this development. It was the beginnings of what we call the Green Revolution. Now, how successful was that? It was not only good for wheat, it was good for corn, it's good for rice. The blue and red are the amount of cereal grains that the world produced from 1960 to 2005. It went up about fivefold. The amount of land put under agricultural production remained the same. Okay? The yield per acre went up. Now, in the United States, the yield per acre went up eightfold. Okay? This was by hybridization, not even genetic. It was genetic modification, but it wasn't molecular genetic modification. Okay? Very profound. That was a technology that was driven by a social need. You're going to face starvation unless you do something. So the Haber-Bosch process, Green Revolution. We have another thing. An unintended consequence of the Industrial Revolution is that we throw up a lot of greenhouse gases, CO2 in particular, particularly dangerous. And this is the temperature variation of the surface, land, and ocean averaged around the world from 1850 to 2014. To most people who look at the graphs, you say, it seems that the Earth is warming up. Only half the people in DC will reach that conclusion when they see the graph. They focus on that little red arrow and said, no, the temperature is constant. And I should also point out that 14 of the 15th warmest years have occurred in the 21st century, but let me remind you, there are only 14 years in the 21st century. Okay? Okay, so now weather is getting weirder, but weather is getting weirder not based on anecdotal evidence, it's getting weirder based on insurance records of losses that are triggered. 1980 to 2012, you try to normalize out the wealth of the world, GDP, and as-built structures. And you still see there's more stuff being lost, okay? This is just a green-eyed shades calculation. You want to charge the cheapest insurance rates possible, but it's to be competitive, but you don't want to go bankrupt. And the reinsurance companies, those are the companies that insure insurance companies in case there's a really big hurricane, a really big heat wave that has crop failures, et cetera. These are the people most worried, because when there's a really big hurricane, they're out a couple $2 billion. And so they keep track of this stuff, and they're saying, hey, something's happening over the last 35 years. I'm going to skip, I don't know, how much time do I have? Okay, I'm going to skip this analogy to smoking and move on to just the following. This is one of my favorite quotes. The Stone Age came to an end not for lack of stones, and the oil age will end but not for lack of oil, said by a former Saudi oil minister. That is not the reason he's the former Saudi oil minister. He said it in the following sense. It said, if you get a better solution, you will transition from oil. We transitioned from the Stone Age to a series of metal ages. You don't look at the stones on the ground and said, those are assets that we haven't recovered. Not every stone in the world had to be turned into a tool, all right? But the converse of this is also true. If we don't find a better solution, economically better solution, you will use the oil and gas because it's money in the ground. So you have to get a better technical solution. So that's why I meant in my title, this is the necessity of all inventions. All right, here's some good trends. Wind is getting really inexpensive. This is wind in the United States, 1980 to 2012. The technological headroom has another 30 or 40% less cost. Now there is a wind production tax credit in the United States, and so there are two numbers I'm going to give you. I'm going to give you one number with the production tax credit. In the Midwest, where we have very good wind, the long-term contracts for 25-year delivery of wind are selling for 3 cents, the low of 2.5 cents a kilowatt hour. If you build a new natural gas plant and the price of gas for the lifetime of the plant, 40 years, stays at $4 a million BTU, it's 5 cents. Now, without the production tax credit, it's about 5.5 cents for wind, okay? It's getting competitive, and within the next 10 years, for sure, it will get cheaper than natural gas without the risk of the volatility of natural gas. Solar has even done better. In July 2008, these are signed power purchase agreement contracts. So this is not environmentalist with wishful thinking. This is a contract. And contracts were being signed in the United States, 18 cents a kilowatt hour to deliver electricity for the next 20, 25 years. By 2014, 2 contracts signed in Texas, one for 5 cents, one for 4.8 cents a kilowatt hour, now comparable to natural gas in studied places in the United States. And in the next 10 years, there's at least a factor 2 headroom in this one, okay? Very exciting. This is wind. Now, I did a back-of-the-envelope calculation, and you see where that arrow is, kind of in the middle range. It said if you had that much average sun per year, how much land would you need to supply all the electricity needs today of the world? And then I multiplied by 10. And that's the amount of land you need in that little square that you can divvy up in many places in the world. Assuming that we stay at the current efficiency, actually the efficiency in silicon is about 18%, but assuming 15% because of losses, okay? You don't need all the land in the world to make 10 times the amount of electricity we will need 30 years from today, okay? It's not that much. We need transmission distribution because if you have solar and wind, you know, someplace, if you over large enough area, like a whole continent, like the United States, the sun will be shining, the wind will be blowing, and so China, because it's got a centralized planning, can actually make long-distance transmission. This is a 2,000 kilometer, 800, plus minus 800 kilovolt DC line. Only 7% of the energy is lost. The highest voltage, lowest loss transmission line in the United States, had you transmitted over that distance, would have lost 85% of the energy. We don't transmit electricity over 2,000 kilometers. That's the point, okay? The technology is here. You don't need superconducting. And Europe is now beginning to plan to distribute its electricity. By the way, that single tower at DC on the left-hand side carries the same amount of power as those towers on the right-hand side. Now, what do you need? Well, you need these high voltage so-called IGBT transistors, and you also need improved dielectrics, so you can put these under the 500 kilovolts underwater, underground. And so our Secretary of Energy, we decided this is something we have to invest in. Better materials for high voltage transistors, better dielectrics. And so as a technical geek in Secretary of Energy, you can actually sit around and say, okay, this is what we need to do. Let's start a funding program on it. This is one of them. It's a prototype. That little transistor, it's a single transistor. It's 1 megawatt power. Let me assure you, you cannot put that on the tip of your finger when it's running. And when I got back to Stanford, I gathered a group together and said, you know, this is fine, but if you can make with a CVD process, a single crystal, and there's ways around this, say a diamond transistor, IGBT, it will be that much better. And so there's a little group of half a dozen that's trying to scheme to do this. I've lost my purity in science. I'm now willing to do engineering because of societal need. I should also say that you don't have to store all the energy in batteries. This is a form of energy storage. This is actually on the symbol of the Department of Energy. When the wind blows, you use the energy to pump water up. When it doesn't blow, it doesn't matter. You got the water. That's energy storage. Okay, here's another form of energy storage. This is a cogen plant. Makes electricity and process heat. Sometimes you need the electricity, you don't want the process heat. Sometimes you need the process heat, you don't want the electricity. So in order to work at an optimum, if you have a lot of electricity, they just use the process and cool big tank of water. This is in Houston, and they use it for air conditioning. And so it's much more efficient. It's catching on. Stanford has its own little power plant that it's building in version 2, and it has tanks of water as well. It's just economically better. This could transform lives. 1.7 billion people in the world don't have access to electricity out of the 7.3 billion. That's a lot. So if you have a robust solar cell, you can do this. Then the first question you ask is, well, you can't store the electricity. Well, what do you use it for? You charge your cell phone. Amazingly, a lot of those people without access, they're willing to buy diesel-generated electricity. It has its own battery. Instead of using a kerosene lantern, you get an LED lantern that's much cheaper to operate, better light, no indoor air pollution, has its own battery. You use electricity to run motors to pump water and to purify it through filters or through UV. You can pump it up the ground, put in a big storage tank, that's your battery. You know, you can get months of fresh water. When the sun shines, you make your fresh water. You don't need a battery for that. What you do need a battery for is to run a refrigerator, but you can have a well-insulated refrigerator that cools a block of ice, and the ice leaks into keep the refrigerator. Most people in third world countries don't want a 8 cubic foot freezer. They do not go to Costco once a month. They want to save food for 1 or 2 days. And so, again, you begin to think hard about how much battery you need, and it's greatly diminished. But you do need a battery. Flaring, this is a total waste. That's a flare in the Balkans. A single flare is as loud as a commercial jet plane. And you're just burning away the natural gas because you don't have a gas pipeline. That's the Bakken shale activity up in the upper left-hand corner. That's Minnesota down there in Detroit. These are images from satellite, but it's worse. That's where it is around the world. Most of it is in Russia. A large fraction is in Russia because it's in Siberia, and they can put on a railroad car and a pipeline oil, but they're not willing to do it for gas. So they burn it. So I was talking to some oil people recently, and I said, here's a thought. Can you put a gas to liquid on a flatbed truck or a rail car, or a couple? He said, oh no, it's inefficient. And I said, no, the energy is free. You're burning it. So it's a gas-powered gas to liquid, to then put it into the oil to ship. So it makes money. That begins to get their attention. Flaring natural gas doesn't get their attention. All right, I'm going to skip this. So I hope I convinced you that the technology for renewable, wind and solar, is getting very inexpensive, and it could be competitive in many parts of the world within a decade. And we're beginning to be competitive in the United States, where the cost of natural gas in the United States is 3 times less than the rest of the world. Okay? So, even today, nighttime electricity is somewhere between free and 2 cents a kilowatt hour. When you go to a world of 50% renewable, there will be many, many days where you have surplus electricity. And I'm projecting, and you may think I'm smoking something, but I think I'll live to see this. Within a decade or two, 2 cents a kilowatt hour for renewable electricity. Half the cost, without subsidy. So we will have abundant electricity. So let's think about, prepare for the future. This is where we're going to head. And so can we engineer industrial chemical process to take advantage of intermittent and very inexpensive electricity? This is the Haber-Bosch problem of this century. First, you want to take electricity and you want to split water to make hydrogen and oxygen. All oil refineries are hydrogen starved. They can make higher value products if they had more hydrogen. We get hydrogen from methane. We reform methane, which is a big carbon emitter. But if you can have really cheap electricity and get an efficient process of making hydrogen, that's a very important step. Beyond hydrogen, can you combine hydrogen with CO2 to make a hydrocarbon starting with methanol? Why would you want to do that? Well, oil ships around the world for a couple bucks a barrel, anywhere in the world. That's why we have an almost universal price for oil. When you put the oil in your country, you have storage tanks of at least 90 days, 3 months, upwards to 6 months. The United States has roughly 6 months of oil storage on our own border. So if you can have renewables where it's cheapest to make, turn into a liquid hydrocarbon there, and then put it on a tanker and ship it, the countries will have energy security, and you don't need transmission lines across the Pacific. There are many countries that don't have renewable assets, Japan, Korea, etc., many parts of India, and just go down the list. The United States has it. Europe doesn't have that much, actually. Okay? This is the technology thing, which I haven't figured out how to do this one yet. I'm thinking about it, but I'm not. But this one is this century's thing. If we figure out that, we're in gold, because now we're beginning to recycle carbon. You can't capture carbon from coal and steel and cement and everything else and bury it under the ground. You can bury it for 100 years, but it's not sustainable. You've got to begin to recycle, close the carbon cycle, and this becomes a way of closing it, based on the fact that we will have cheap energy. So when I give talks to young people, I say, if you want to invent something, this is it. You want a small potatoes, invent a 5 times better battery. But if you really want to, that will partially change the world at a 10% effect, but this will change the world in a very profound way. I'm going to skip that. I'm going to skip this. These are methods that we and others are looking at. So we're going to rephrase this in a cartoon form. Captured CO2, you split water, you combine the two. Those molecules on the right-hand side are what we use in gasoline and diesel fuel. They're hydrocarbons, C double bonds, and CH bonds. Electrochemistry, photochemistry, I don't know. We haven't figured this out, but that's the challenge of this century. I tell my students, I told the people that I brought into the Department of Energy, the following: the greater danger of most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. So I'm putting out very big challenges. Actually, Michelangelo said that. Finally, I'm going to end with this picture. Taking Christmas Eve, 1968. The mission before Apollo 11 has orbited the moon to prepare for the moon landing. The astronaut, the fourth orbit, they turned the capsule earthbound, and the astronaut who took this picture said, "We came all this way to explore the moon. The most important thing is we discovered the Earth." The moon is not a good place to live. From this vantage point, Earth looks pretty good. And guess what? Nowhere else. Now, since 1968, there is very compelling evidence the climate has changed and humans are causing it. And so this is the great invention challenge that we need. And I'll close with this. It's an ancient Native American saying, we do not inherit the land from our ancestors, we borrow it from our children. And we are taking out deeper and deeper mortgages for each succeeding year. Thank you.
So we're going to skip questions because we're running late and we have buses and everyone needs to go upstairs and to go to the California Science Center. It's going to be exciting. Great. Thank you so much for coming here. So Dr. Shu can't stay here for the event. He's one of our new fellows and you won't be able to be here for our ceremony tomorrow. So we've done this once before for Bob Langer, who was our keynote speaker at our first conference, and we're doing it again for Steve. We're going to give you your fellowship now, okay? And there's more stuff out there when you get out. But this, you know Maury from Caltech. And so, Maury, you can give me that. This is our trophy we give. And this is for all you to see what you're getting tomorrow, so. Well, that one's glass. But wait, there's more.
It's like the late night TV ads.
So we do, as we talked about, the fellows wanted a medal, and so this is the medal from the National Academy of Inventors.
Come on, to a man who's won the Nobel Prize, that's nothing.
Yeah, well, it's okay. Go
That's
ahead,
not true.
So congratulations. Thanks for being with us. And we've got a pin out there. That's great. And you're coming tonight?
Yeah.
Great. Well, thanks. So we're going to break, and we will meet at the buses, and then we'll have a great night at California Science Center. Thank you.